Welcome back to part two. This is chapter 7. I'll go ahead and put that in there. Part 2 for our chemistry with engineers. And this we are beginning on slide 12 in this list. And now what we're going to do is we're going to look at something called resonance structures. Resonance structures can be drawn when the choice of a double or triple bond location is arbitrary. So it could go in two different places. The positions of all the atoms are identical. Only the position of the electrons are different, and that's basically in the double bonds and the lone pairs. The actual structure is a resonance hybrid, an average of the contributing structures, not a mixture of them. So let's go ahead and take a look at how we would do this with a couple different options. Let's start with SO2. Sulfur dioxide. Okay, so sulfur is right under oxygen, so it has 6 valence electrons, and then we have 2 times our oxygens there, so we have 18 valence electrons. Okay, so first of all, sulfur is under oxygen, so we know that it's going to tend to form this structure like that. So we can go ahead and start with that. So now I have 2, 4, 6, 8, 10, 12, 14, 16, and 18. Okay, so now the problem here is that this, so we're going to call this oxygen 1, and we'll call this oxygen 2. Okay, so, and the problem now is that oxygen 1 has a complete octet, but oxygen 2 does not. So what we're going to do is we're going to move in one of these pairs from the sulfur like this, okay, and create a double bond to share, just like that. There. Now I have 8 electrons on all of them. But that the double bond needs to go on oxygen 2. You can draw basically these arrows that say we're going back and forth, and you can draw the exact same structure, but basically with everything backwards. Okay, and I've just basically made the electrons equidistant, and now you can see that the double bond is on oxygen 1 instead of oxygen 2. And what's happening is those extra electrons, the extra electrons are going back and forth between the two pretty much constantly. They're delocalized. Okay, so now let's look at doing this with ozone as well. So we have O3, okay, and so that's 3 times 6 or 18 valence electrons again. And actually, this is going to look just like the other one, except that we have an oxygen in the center. And so we'll go ahead and say, okay, so here's ozone. One of the reasons that this happens is because oxygen, oops, I put too many on that one. Oxygen um, doesn't like this structure over here. It doesn't like to have 3 bonds and 1 lone pair, and it doesn't like to have 1 bond and 3 lone pairs. That doesn't give it a formal charge of 0. We're not getting into formal charges in this class, but it's not real stable. And that means that this oxygen here is the one that is the most stable. Okay, and so we'll have this, it'll go back and forth on a resonance structure where that double bond then moves. And sometimes students will say, do I have to draw them both? And the answer is yes, you have to draw them both, because that's the point, is to show that they both exist. Okay. So now we are up to slide 13. And there we go. In our discussion of resonance, and we're looking at what's called a benzene ring. Benzene is C6H6. It's a very common solvent. And in this benzene ring, you can see that you have double bonds here and here and here. And then you have single bonds here and here and here. And then over here, it changes, and you have single bonds in the basically the opposite locations. So the double bonds have just moved over one. And what people will often do is they'll write benzene like this. And here we have our hydrogens, like so, and we'll kind of draw a circle in here to show that it's everywhere. Another option that you'll see instead of the circle is you'll see dotted lines like this to show, instead of showing both resonance structures, the dots show you that you have partial double bonds kind of everywhere. All right, so those are some other options for how you would draw resonance structures for benzene. Okay. Now let's take a look at expanded octets. So if you remember, once you get down to n equal to 3, you have a 3D orbital in n equal to 3, but it's not filled until after 4s gets filled. So that means that for every row beginning with n equals 3, you have unused d orbitals in that energy level. So for our non-metals, what we can do sometimes is we can expand their octet and they can have more than 8 electrons. But again, they have to be larger elements. They have to be n is equal to a 3 or bigger. So let's go ahead and take a look at these. So first of all, we have SF6. So first we count our valence electrons, and that's 6 times 7. So we have 42, and 6 is 48 valence electrons. Now the SF6 means that we have a sulfur in the middle. Okay, and we have 6 fluorines around it. And I'm going to go ahead and place them like this. And you can see automatically how now you have all of these electrons on your sulfur, and you actually have 12 valence electrons on your sulfur. It's expanded, it's octet. Now we have 48 valence electrons here to play with. So let's go ahead and see how many we can get out. So far we have 12. And so then I'll start down here, and we have 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, and 44, 46, and 48. There we go. We are done. We have all 48 electrons on our sulfur. Okay, so now let's look at SF4. Okay, so here we have 6 electrons from our sulfur and 4 times 7 for our fluorine. So that's 28, and 6 is 34 valence electrons. Okay, so now let's place this one. Okay, this is going to be a little different. So we have our 4 fluorines on our sulfur, and let's see, right now this looks like we're obeying our octet. So let's see what happens if we start placing our valence electrons. And this is the kind of molecule where it's really important to count those valence electrons, because you're going to see that there's a little trick there at the end. So right now we have 8, and now we're going to go 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Now, you haven't been counting your valence electrons. You're going to look at that and say, hey, I got 8 on sulfur. I got 8 on each fluorine. Octet obeyed. Hurrah. But you've only put 32 valence electrons on it. and we've counted 34. So we need to put them somewhere else. And we can't expand fluorine's octet because it's only an N equal to 2. So what we're going to do is we're going to sneak them in and we're going to put them right there on the sulfur. So let's come here to our arsenic pentabromide. Okay, and for this one, arsenic comes with 5 valence electrons, and now we have 5 times 7 for our bromine. That's 35, and 5 is 40 valence electrons. And this one's going to look a little bit easier again because we have 5 bromines on our arsenic. So we'll go ahead and place them 1, 2, 3, 4, and 5. And here's our fluorine. Oop, these are bromines, not fluorines. Let me change that. Okay, now I have 10 valence electrons on my arsenic, and let's go ahead and place the other 30, right? Okay, so we've got 10 here, and we need 40 total. So let's see where we're going to get to. So we've got 12, 14, and 16, and notice they're going in pairs, and then 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. So now I've placed my 40 valence electrons. So these are some examples of how we would expand our octet. All right, so let's take a look at the concept of our shapes of molecules. Okay, and we are on slide 15. Keeping track. Okay, so molecular shape is always going to be in 3D. We don't live on paper, and that makes things a little bit difficult. The molecular shape affects our reactivity, it affects boiling points, it affects melting points, it affects all kinds of really important things. Okay, so we need to know what it's going to look like. It's also really important because knowing what it looks like helps you understand how the reactions are going to occur. Like a long chain might have something coming at it from above, or a branched chain might have something coming at it from the side. And so you need to know where the atoms are. Okay, so based on that, our molecule assumes the shape that allows them to minimize the repulsions between the electron pairs. So remember, here we had our oxygen, and here and here, and here and here, and there you go. Well, these are going to push apart on each other. Okay, and now here you notice a couple words here. Here you see lone pair electrons, and these are lone pair electrons, and one pair equals 2 electrons. And then here, remember, this is a bonding pair, okay? And here also 1 pair equals 2 electrons, okay? All right, so now let's take a look at the shapes of these. And we are up to slide 16. Okay, so first of all, some molecules like beryllium chloride and carbon dioxide are going to form linear molecules. They share 2 electron pairs and they have a bond angle of 180 degrees. Okay, and beryllium chloride will look like this. Okay, and you can see how that bond angle is 180 degrees and works for beryllium chloride. Beryllium chloride is one of those elements that fails to meet the octet rule, okay? And so it's also an exception, and it's happy with only 4, and that's because it only has 2 valence electrons and it only has 4 total electrons. It's very small. And now you're going to remember carbon dioxide, which looks like this. You already kind of have these in here for most of what I'm going to be showing you, okay? And you can see how this one also has this linear bond angle. Okay. Now, boron is also very small. And if you remember from back when we were looking at how many valence electrons it has, you can see that it only has 3 sites for bonding. So it's also an exception that is going to fail to meet the octet. Boron is only going to have 3 electron pairs, and it's going to look like this. This is boron trifluoride, and we'll place its electrons like so, always in pairs. And it is going to have what's called a trigonal planar and a bond angle of 120 degrees. We'll be working with these ball and stick models in the lab as well. All right, here we are at slide 17, and let's look at a few more shapes. Our next shape is a tetrahedral CH4, and we've seen CH4 drawn before. In fact, you've seen all of these drawn before, so I'm just kind of showing it. Okay. Now, this looks like it would be perfectly symmetrical, except for the fact that it's not 2D. So the best way to get these apart from each other is to form a tetrahedron. And you can see this sketch drawn here. Okay. And each one of these bond angles, in case you can't see around what's going on here, is 109.5 degrees. And we're sharing 4 electron pairs, and it is called tetrahedral. Now we have a trigonal bipyramidal, okay? And you can see here that what's going on is that you form this triangle here in one plane, and then you have these sticking up above. So let me draw that arsenic pentabromide that we had before, but let me draw it with the structures that we have here. Okay. And then up to the bromine and down to the bromine. And now you can see it kind of forming, here you can see the triangle. And the bond angles on the triangle here are 120 degrees. And then you can see how it kind of goes up and forms this tetrahedron up like this. And this bond angle is 90 degrees. And then it's going to form this other tetrahedron down like so. Well, sorry, this other pyramid, not tetrahedron. Tetrahedrons are up here. This other pyramid. And this is also going to be 90 degrees. Okay. And then the bromines would have lone pairs on them. But here I'm just sketching out your shape. And so that one has, okay, so tetrahedral has 4 electron pairs here. A trigonal bipyramidal has 5 electron pairs. Okay, and here's its name again. Now, octahedral has 6 electron pairs, and it forms an octahedron that looks like this. The bond angles are 90 degrees unless we're going all the way from top to bottom. That's the only 180 degree in there. And then you could imagine the SF6 drawn in the same way. Let me see if I can sort of show it like that. And that forms kind of that square in the center like this. And then we can come up here and form our fluorines here. And then you can see the tetrahedron that it forms like so. Not tetrahedron. Sorry, I keep saying tetrahedron. It's a tetrahedral. It's a 4-sided pyramid on the top and the bottom, just like that. And each one of these is 90 degrees, and it's 180 if we look from the top fluorine to the bottom fluorine. So there you have a couple of expanded octets shapes. So this one, we are up to slide 18, and this is going to show us a few of what we're looking at. Okay, so let me kind of explain how this works. So here we had our beryllium chloride and our carbon dioxide, okay? And then on this one, we had our BF3. But now let's look at this one here. Remember ozone? Ozone looked like this. And I'm just going to draw one resonance structure. Okay, so this lone pair counts. And so it has a trigonal planar electron arrangement. This down here, it has a bent or angular shape. So let's look at another one of these possibly. So here you have a tetrahedron, and the X's all stand for an atom. And an example of that might be that CH4 that we had drawn. But now let's look at this. Hang on, I've got another slide, and I think I have some of this on the next slide. So it's we'll get, I don't have a printout. So I think some of this is on the next slide. But see how in this one you have one little dot pair up there. So an example of this might be ammonia. Let's see. Let me bring this out here. Okay, and an example of this might be ammonia like this. Okay, and that has a tetrahedral electron arrangement, and the shape is trigonal pyramid. So that's the way you do that. So it's a tetrahedral shape. Sorry, a tetrahedral electron arrangement. I said the wrong thing. Tetrahedral electron arrangement. And it has a trigonal pyramid shape. So you always have to be thinking about what's what. Okay. You could also say, for example, this one right here is an example of water. See? Okay. So this also has a tetrahedral electron arrangement and a bent or angular shape. So I'm pretty sure this is slide 18, just to help you out here. Okay. So you have to Lewis structure and then think where it is. So for example, this, to kind of show you how these match, you have these two lone pairs here and here. Okay. And then you have, here's your elements here and here. And so it's that tetrahedral electron arrangement here. And then it's bent or angular for the shape. And that's kind of where that all comes from. All right, let's do a few more and then we can be done with this chapter. Okay. Oh, great. So none of these I did already. So what we're going to do is we're going to walk through these and be looking at them in terms of what's on the slide. So I'll kind of I'm going to show some of the shapes very quickly because I've already done them. So first of all, SF4. Okay, so SF4, you remember, had the 4 fluorines on it. It is. I do have some notes. Okay. All right. And remember that it had the fluorines here like this. And then it had dots. And you'll see that what I did is I moved the 4 fluorines over so that I was making room for an extra lone pair, just like that. Okay, so now what we have is we have this lone pair paddle coming off like this. So that means that the electron arrangement for this is trigonal bipyramid. And if you look at the previous slide, those printouts, you'll see that this goes along with a shape that is seesaw. If you if you didn't have any if you didn't have any lone pairs on the central atom, they would match. Okay. All right. Now let's take a look at our next one, which is BRF5. So that one we'll need to kind of start from scratch on, BRF5. So we have 7 valence electrons plus 5 times 7, that's 35, and 7 is 42 valence electrons. Okay. And let's go ahead and think about our bromine. So we've got 5 on it. 1, 2, 3, 4, 5. Okay. And now we'll make our dots. So for our electrons. So here we've got 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, and we need 42. So we put those on the bromine there. Okay, so let's think about what this is going to be now. And we'll have that paddle there. So now I've got 1, 2, 3, 4, 5, 6 things on my bromine, which means that my electron arrangement is going to be octahedral. And my shape is going to form what's called a square pyramid. And you can see what that looks like. You can see the shape there on the previous slide. Okay. So now moving along, let's take a look at what happens with an ion. So I have 2 ions on here. One is PO4 3 minus. Remember, this is phosphate. Okay. Now let's take a look how we would work this. So phosphorus has 5 valence electrons. We have 4 oxygens at 6 each. And now this 3 minus means that we're adding 3 extra electrons from our charge. Okay. So 4 times 6 is 24 plus 8 gives us 32. Oop, that didn't come out very clear. Gives us 32 valence electrons. Now, because it's an ion, we have to start with some brackets. Brackets says ion. All right, and 3 minus. Now we have our phosphorus, and we're going to place our oxygens around it, just like that. Okay. And now I have 8 electrons accounted for, and I need to place 32. So I have 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. Okay. And this is a completely legitimate Lewis structure. If you're taking general chemistry, you would have to learn about formal charges, and then you would actually find that the actual structure for this brings this in like that to form a double bond right there. And that really makes sense because do you see how we have 3 negative charges? That means that basically we have a little negative charge here and here and here. And that's where that's coming from. Okay. But the original one that I showed was completely fine for this class. Okay. Let's look at another one. Let us look at the next one on this list is PCl5, and that has 5 valence electrons plus, for the phosphorus, plus 5 times 7 for the chlorine, or 40 valence electrons. And so let's go ahead and start placing. We have phosphorus with our chlorines like so. And we have 10 so far, and 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. Okay. Our phosphorus has an expanded octet here. Okay. And it is then going to, now there are no lone pairs on the center atom. And when there are no lone pairs on the center atom, that means that the electron arrangement and the shape are the same. And in this case, that is going to be a trigonal bipyramid. You know what I just realized is that I forgot, go back to your drawing for your phosphate here. This one had four things on it. And so the electron arrangement and shape were both tetrahedral. Okay. So you can add that to your picture from before. All right, two more here, and hopefully you guys are starting to feel like this is making sense. Next, we have ONF, and it's a little hard to know how are we going to draw this as a picture. Okay, and the easiest way to draw it is basically to draw it in this order. Okay, so we have 6 valence electrons from our oxygen, and we have 5 valence electrons from our nitrogen, and 7 from our fluorine, which gives us an overall 18 valence electrons. We're going to begin by placing just like that because we're not exactly sure what this is going to look like. All right, so far that's going to give us 4 electrons. So let's go ahead and figure out where we're at now. We'll start with fluorine. Fluorine, remember, can only have 1 bond and 3 lone pair electrons. So we know that fluorine is going to have to look like this. All right, so now I have 10 electrons and I have, so 2, 4, 6, 8, 10 electrons. Okay, and I have 8 left to place. So we could go, there's 2, 4, and 6 and 8. Okay, that's my 18 electrons. Now, but if I look at this, I can see that my nitrogen has 8, but my oxygen only has 6, which means I'm going to have to bring a pair in like this, just like that. And now I have 8 on my nitrogen, 8 on my fluorine, and 8 on my oxygen. And when I'm drawing this, I would say, okay, don't forget this paddle up here. And what that means here is that this is going to have an electron arrangement that is trigonal planar because it has 3 things on it. And again, you can see all of these on that previous slide, that chart. And it means that my shape, because of that lone pair, is going to be bent or angular. You really only have to write one word. Okay. All right, now let's take a look at our last one. It's mighty tricky. And I'm going to draw it so that you can see it just as easily as possible. Okay. So here we have our BRF4. And notice that there's a minus sign here. That means that this is an ion. Okay. So our bromine has 7 valence electrons. Each fluorine has 7. And we add 1 electron there from the charge. Okay. So that gives us 35 plus 1 is 36 valence electrons. And we have to put this in brackets because it's an ion with the charge out to the side. So let's take a look here. What I'm actually going to do is I'm going to kind of draw it like this because I know that if it was BRF4, like 8, so 8 on each one of these 4, 8 on each fluorine like this would only be 32. Okay, because 8 times 4 is 32. So I know I have 4 extra. And so you can sort of preview it with your math a little bit. So I put in my dots on my fluorine because my fluorine has to look like this with its pairs. And I can see here that I have 32 valence electrons. I have 36 total. So they're going to go on the bromine, just like that. And so I'm going to be like, actually, I don't want that to be quite so heavy. There we go. Let's try this again. Okay, there we go. And what this looks like now, it's a little bit tricky to see, but you have that square in the center, and the lone pairs act as your pyramid shape, like that. Okay. And so that means that your electron arrangement is octahedral. But if the lone pairs stick up and down, and everything else is right there in the center. So the shape for this is square planar. Okay. And that concludes our chapter 7. I will see you in class.